Good afternoon, everyone. My name is Jay Lee, and I'm the CTO at ATX. I'm going to deviate a little bit from technical talk, and I'm going to talk a little bit today about a economic model that we worked on with a partner MSO customer probably about over a year ago, and it really explored or took a look at how MSOs might maintain their taps and passives portion of their HFC network with two different options. Maintain it the way they always have, which we would call a legacy mode, which is really as cost effectively as possible, or at least it might look as cost effectively as possible. Or the other approach, which is we call evolutionary mode, where you actually start to seed your network with, on every maintenance call, you start to take out existing taps and passive devices and start to seed your network with 1.8 gigahertz capable equipment. All of this obviously in the context of an MSO's journey to upgrade their network to be able to support DOCSIS 4.0 1.8 gigahertz. So I'll just talk a little bit about how we built the model. On the left side of the screen, we took a look at the maintenance drivers the items that really drive the maintenance aspects of the networks. One of the big ones was actually loose connections in loose screws in taps and passive devices. We also have failed faceplates where in a tap type device, if the faceplate fails, just the faceplate needs to be exchanged out. Or in some cases, we have full failure devices where a brand new device needs to be spliced into the hardline coax. And what we did is extracted from that two different approaches as to how we would deal with those maintenance mode activities. As I said earlier, one mode was what we called legacy mode. So that meant if a technician went out to fix a location that had loose screws, they would simply tighten the loose screws. If it was a faceplate that was damaged in some way, just the faceplate would be upgraded. So, and if a device had to be pulled out of the network and replaced, it would be what we would call legacy 1.2 gigahertz technology devices that would be put in, which would be less costly than 1.8 gigahertz type devices. And I'll go through some of our cost modeling in the next slide. From an evolutionary standpoint, what we modeled was every time a technician rolled up to a maintenance issue, whether it was with a tap or a passive, that device would automatically be removed from the network, and the entire device would be replaced with a 2 gigahertz capable tap or passive. The model that we generated was over a 5-year time horizon. So at year 5, the concept was that the entire taps and passives portion of the network would be upgraded with 2 gigahertz capable devices so that the entire network could support DOCSIS 4.0 1.8 gigahertz to its fullest extent. Just before we get into some of the details around the costs, this was one of the interesting findings in this study. This is actual data from one of our MSO partners. They had started to collect information on what the sources of maintenance mode activity was, and they actually found a 0.2% failure rate with respect to loose screws, either the screw down on the hardline stinger would back off itself, or technicians would forget to tighten it down. 0.2% doesn't sound like a lot, but as you can see in the table in the top right, depending on how big your network is, it translates to many truck rolls a day that are really potentially avoidable. One of the things that's a benefit with 2 gigahertz type devices or 1.8 gigahertz type devices, and not just ATXs, I think all of the manufacturers of taps and passive devices to attain frequencies that hit 1.8 gigahertz or extend beyond. The actual mechanism with which the stinger from the hardline coax interfaces with the tap or passive device will not involve screws any longer. Most designs will be some type of barrel with a spring-loaded mechanism that would engage on the hardline stinger. So inherently, that's a huge benefit with respect to removing a legacy device and putting in a new 2 gigahertz capable device. That whole loose screw phenomena disappears. So just with respect to some of the modeling we did, I apologize, I thought I would have a pointer, so I'll have to talk through it. But in the top left is how we modeled a given MSO's network. For this presentation, we chose a 10 million homes passed network. The model's totally scalable, and by the way, we make it available to anybody who's interested. But from the number of homes passed, we basically had some estimates with respect to how that would manifest itself in terms of numbers of taps and passives in the network. We took number of homes passed, divided it by 4.5 to get to our number of taps as an example, and our ratio of taps and passives is a 3 to 1. So that's how we basically calculated this out in a 10 million homes passed network, where you can see our total taps are 2.2 million, our total passives are 740,000 for a total of almost 3 million devices in a 10 million homes passed network. As it relates to the failure profile we projected onto this network, we took in aggregate about a 1% failure rate. 0.2% of that was the loose connection side of things, and then 0.8% was whether it was a full device or a faceplate type of failure. We also modeled in that out of that 0.8% failure rate, that 25% of that 0.8% was actually a faceplate issue, as opposed to an entire device that would have needed to be addressed on a maintenance mode basis. On the right-hand side of the chart here, we basically outline the cost inputs associated with both materials and labor. And what we did for this particular exercise is we normalized all of the costs against what we call legacy 1.2 gigahertz tap device. So we called that device $1, and we extrapolated from that $1 to the other costs associated with the maintenance mode or upgrade activity. So as an example, you see a faceplate is 75 cents. As opposed to $1. From a labor perspective, two key elements are on a targeted maintenance mode, on a targeted maintenance activity, we have that at 8 times the cost of, or $8.30, which is 8 times the cost of the tap material, and that's really when it's a one-off maintenance mode issue and a technician needs to roll a truck on a one-off basis. Another important cost we factored in here is the bulk rate to actually upgrade an entire node serving area, which would contemplate that technicians are rolled out to that area and upgrade the entire node serving area, and replacing or maintaining or replacing the taps or passives. The other important piece here is the 2 gigahertz taps devices we modeled in at a 30% premium over what we call the legacy 1.2 gigahertz. So when we ran this model, this is sort of a summary of the maintenance activity that occurs in the plant over a given year. So in this, and once again, this is for a 10 million homes passed network. It scales linearly. we saw the total number of location visits at almost 30,000 in a given year. And you can see the breakdown with respect to the 0.2% and the 0.8% in terms of loose screws versus faceplate upgrades or device replacement. This is how the maintenance cost per year played out. And once again, we looked at it from a legacy mode perspective and an evolutionary mode perspective. Definitely the legacy mode of operation on a per annum basis is more cost effective, but it's not tremendous. And I don't think that should be particularly earth-shattering, given the price points of these types of devices relative to the labor costs associated with dealing with these, either fully replacing them at 2 gigahertz or replacing them at 1.2 gigahertz. There's labor is just massively dominant in the expenditures to the tune of 85 to 90% of the total cost in either scenario. So what does this look like by the time we get to year 5 in terms of completely upgrading your network to support 1.8 gigahertz? This shouldn't be particularly earth-shattering either. I mean, we've got a 1% failure rate over 5 years. So in one instance, in the evolutionary mode, 5% of your network has already been upgraded with devices that support 2 gigahertz passband capability, whereas in the legacy mode, if you continued for those 5 years maintaining in legacy mode, you have to upgrade every device that exists in the network. So you can see in this case, there is actually a benefit by the time you get to year 5 and execute that full network-wide upgrade, that there ends up being a cost savings in adopting an evolutionary type of maintenance mode activity. And from a total cost perspective, from day 1 to end of year 5, this is how these numbers play out. So had we operated in legacy mode and waited to upgrade the network at the end of year 5, you're looking at a cost of about $12 million, $12.2 million. Whereas if you had adopted an evolutionary mode type of approach, your cost is $11.8 million. Now, it's small from a percentage standpoint, 3.2% in this case, but remember that this is all normalized to a tap device that is priced at $1. That $388,000 worth of savings is probably more on the order of $6 to $7 million that you could save over the 5-year period that we explored. So from our perspective, we fully believe that adopting a evolutionary mode of maintenance mode activity around taps and passives in your network makes a ton of sense economically. One thing I will point out that this model did not capture the fact that when you put in a 2 gigahertz device, there is no longer a loose screw issue that occurs at that location. We think actually, as we're finding out more, collecting more data, that the 1% failure rate is actually smaller than what reality is, and that technicians are visiting these locations more frequently than that. So that would only strengthen the case for the evolutionary mode of operation. We think there's obviously just some inherent advantages to technicians becoming familiar with the latest and greatest technology that's available, and seeding it into your network provides a number of operational benefits. And that is the end of our discussion. Thank you. If if anybody is interested, there, in the presentation material, there is a link to a white paper on this, and further, if anybody would like the model, we're more than willing to share it, so please feel free to contact me. Thank you.